Okay, we're very happy to have Mateusz Łewyk from Warsaw speaking on varieties of truth definitions.
Thank you very much, Athar. It is always a pleasure to be here. So as you can see, this is a joint work with my former master student and currently my PhD student, Piotr Gruza. And what is it all about? So let me start with some basic definitions. I will start with a definition of truth. So by this, I mean any sentence. Sorry, let me try. Any sentence theta in some language L said that some formula in the language of this sentence serves as a definition of truth for arithmetic. So probably from the sentence it follows that this formula capital theta satisfies all the Tarski biconditionals. And for the sake of simplicity, we shall assume that all our definitions extend the basic arithmetic, the elementary arithmetic in this case. What's important that this is finally axiomatizable. And I will use two short forms. So this capital def denotes the set of all definitions of truth for the language of arithmetic. And CDEF denote the set of definitions of truth which are conservative extensions of EA. Right, so let me now pass to the next slide. Oops, sorry, I didn't want this. Right.
I'm sorry,
So
could you just remind me what EA is?
EA is the I delta 0 plus exp for us. Yeah, sorry, this is short. So EA typically stands for the elementary arithmetic, and this is indeed ambiguous because one can mean either like an equivalent, a version of PRA, primitive recursive arithmetic, but just for the first level or the second level of the Grzegorczyk hierarchy, meaning the terms that you can define only from the exponential function. And this is typically a theory in an infinite language. By EA, I mean just I delta 0 plus exp.
Thanks.
Okay, so examples. So CT minus of x denotes the following formula, which is an extension, which is a conjunction of the following four sentences with EA. So what you will see is just the statement that a fresh predicate T satisfies the inductive Tarski truth conditions for sentences of depth at most x, where by depth I mean maximal nestedness of connectives and quantifiers. So I count every single connective and every single quantifier on a branch in a syntactic tree, and this is a depth of a formula. Right, and except for T, all the formulae that occur in these axioms, they are arithmetical. Right, so let me start. So an atomic sentence is true if and only if both terms get the same value. A negation of a sentence of small depth is true if and only if the negated sentence is false. If I have a conjunction of small depth, then it is true if and only if both conjuncts are true. And if I have a quantified sentence starting with a quantifier of small depth, then it is true if and only if it can be witnessed by a numeral. This Z dot denotes a canonical numeral for number Z, which makes phi true. Okay, so, oops. So CT minus denotes the sentence saying that for every x, this T is a good truth predicate for all depths, and this is one of the most canonical theories of truth. This is also a truth definition in my sense. This is a finite sentence which obviously from which you can derive all the Tarski biconditionals. So let me give you something different. So now what is different? So PT minus differs from CT minus by resigning from this global axiom for the negation. And instead of it, you independently, so for each connective separately, you say how it behaves when negated. So double negation can be erased. Negation of a conjunction behaves in a De Morgan law, in a De Morgan way. Negation of the existential quantifier as well. And except for this, we have standard axioms for atomic sentences, conjunction, and the existential quantifier. And maybe say once again, this is all just for arithmetical sentences and formulae. And as one can easily show, this is a different truth definition, at least syntactically, right? By external induction of the formula complexity, you can actually prove that all the T biconditionals can be derived from the conjunction of these axioms. So the idea behind this theory is the following one. So if you read all these equivalences from right to left, you actually get instructions of a process of determining larger and larger sentences of greater and greater complexity to be true. So you can actually think of this as the description of a process of learning the truth. And for example, it says that if you know that the negation of one of the conjuncts is true, then the negation of a conjunction should be true as well, right? And the direction from left to right says that essentially T is a fixed point of this process. And this fixed point can be obtained because these conditions are positive in T. So in fact, it describes a positive monotone operator. So it will reach a fixed point, and that's the idea behind PT minus. Let me maybe say one more thing, is that from this perspective, if you think of this T as a process of gaining new knowledge about which sentences are true and false, and which are false, and this axiom for the negation from CT minus is no longer that natural because T of phi, it essentially says that there is a stage of this process such that phi is classified as true at this stage, right? So if T is not classified at some given stage as true, then it might still be classified at some later stage. And still, we also don't have we cannot guarantee that actually this process will determine the truth or falsity of every possible sentence. Okay, so these are the motivations.
Mateusz, shouldn't there have been also a negative clause for the atoms?
Yes, I think it should be. Yes, obviously. Sorry.
Okay.
Yeah. Thank you very much. Right, and then the main question I'm trying to answer or try to understand more about is that how many different truth definitions are there? So let me just ask whether these two are essentially different. And in the meantime, I will explain what do I mean by being essentially different. So first remark, it is easy to see that actually CT minus proves PT minus. That's an easy exercise. However, the converse fails in a pretty strong sense. Namely, there is no form, not only PT minus doesn't prove CT minus, but even it cannot define a truth predicate, which provably in PT minus behaves like a truth predicate for CT minus, right? So there is no formula theta such that when you translate T as theta, then all the axioms of CT minus becomes provable in PT minus, right? And this follows from two basic facts. So from what I told you already, actually you can do the fixed point argument showing that every model of PA can be extended to a model of PT minus. And this is not specific to PA, so each model of PA will be good. However, by far not every model of PA expands to a model of CT minus, because by Lachlan theorem, CT minus imposes recursive saturation. So if a model of PA expands to a model of CT minus, then this model is recursively saturated. So then if we had such a definition of CT minus to predicate in PT minus, then we could extend and we could expand every model of PA to CT minus, in particular a non-recursively saturated one, which is not true. Okay? And this will be my measure of, this will be my criterion when the two theories are different. Namely, they cannot interpret each other, or one of them cannot interpret the other one. Sorry, cannot define it. There's a question, right?
Yes. This is really so I know this is not the focus of your talk, but this part is really interesting. Every model of PA can define this sort of truth predicate in this PT minus sense, but not, well, not defined, but can be expanded to a model of PT minus. So what, I guess this is not so much a well-formed question, but what's missing, right? Like obviously a model that's not recursively saturated will not have a truth predicate in the sense of CT minus, but so this T that you define and or that you build, you construct on your non-recursively saturated model, what does it look like and what is it missing so that it's not a model of CT minus?
Yeah, that is a good question. So typically, for example, if you do the fixed point construction and you look at a minimal, the previous one, a minimal fixed point of this operator. So this construction goes as follows. You start from the empty set, then you add all the true atomic sentences, the negations of all the false atomic sentences, and then you go further and further by formula complexity. So in particular, if you start in a countable model, then at some countable stage, you will reach a fixed point, because otherwise you could create like an uncountable chain of elements of this model if all the inclusions were strict in this chain. And actually you can show that this the truth predicate constructed in this way leaves a lot of sentences undecided. So in particular, you can show that if a formula starts with a non-standard block of negations, then it is neither true nor false. And this can be verified simply by showing that there is no stage in this construction where either it enters or its negation enter, and this, I mean, essentially followed by well-foundedness of this process.
So you're only putting in the minimal amount, you're only deciding the minimal amount of formulae that you need in order for it
Yes.
to satisfy these. And so these things with non-standard blocks at the beginning, right? That makes sense. Okay.
Mhm.
Yeah. Thank you.
Right. So now the definition of the definability, and this is just a generalization of what we had previously. So if you have two sentences, then we say that theta 0 and theta 1, we say that, they are in languages L0 and L1 respectively. We say that theta 1 is definable in theta 0, sorry. If there are L0 formulae, theta 1 up to theta n, such that if you substitute theta 1 for the first non-arithmetical predicate of L1 and in general theta I for the ith non-arithmetical symbol of L1, then theta 1 becomes provable in theta 0. Right? So this is an example. In fact, we can say that theta 1 is definable in theta 0 if there is non-relativized direct interpretation which leaves the arithmetical part untouched, which is the identity on the arithmetical part of the language of theta 0 in theta 1 and theta 0. Right? Oops, sorry. Okay, so we say this is how we denote that theta 0 is definable in theta 1. And we think of the one which can define theta 1 if it can define of theta 0 as of a larger true definition, like a stronger true definition. And one remark that this definability is a pre-order on the set of the definitions of truth, and henceforth we shall identify mutually definable definitions. Okay, and my main question is, what is the structure of this definability relation on the set of conservative definitions of truth? Why I specialized to conservative definitions.
I'll have the bit of lobster rolls.
So were there a question or just unmuted remark?
I think someone just unmuted by mistake when they joined.
Okay. So this is because I do not want to allow for straightforwardly copying the Lindenbaum algebra of EA into the structure of these truth definitions. So without this restriction on CDEF, you could conjunct your truth definitions with unprovable sentences in EA, and so this way, if they are, for example, mutually independent, and create different definitions of truth, and I don't want to disallow such cheap tricks and focus just on, say, the truth theoretical content of these definitions. Okay, so now this concludes the preliminary part. Let me talk about the structure of the definability. So first remark is that the set of conservative definitions of truth, conservative over EA, with this pre-order, this is a countable distributive lattice, and it is actually not that hard. Actually, this is a good exercise to show that that suprema and infima exist. In this case, it uses some classical theorems and very basic. And as I learned quite recently, and I verified this today, there is a answer to our problem from the paper by Ellie Gatsby, which shows that actually you can adapt a density argument for Lindenbaum algebra, showing that actually each proper interval, so by this I mean that there are at least two elements, alpha and beta, in the structure of definitions of truth, this might be infinite. You always find intermediate truth definitions. And from this point, I will focus more on the structure of this CDEF as a lattice, and I will work with the following kind of truth definitions. So CT minus restricted to phi, where phi is a formula in the language of PA. It says that we have EA as usual, and then CT minus holds as long as phi holds. So for all numbers which are in the extension of phi, which is in the set definable by phi, we have a truth predicate which holds for sentences of depth at most x. And an easy remark that if we have a true pi2 sentence, meaning that phi of x is sigma 1 and it holds that for every x phi of x, then by sigma 1 completeness, such an object is actually a conservative definition of truth. So since CT minus by itself is conservative extension of EA by Kotlarski, Krajewski, and Lachlan, and many other proofs, Visser, Lee, Cieśliński, Pachomov, and so on. So we have good evidence that this is indeed conservative extension. And these all theories, they are actually sub-theories of CT minus. They are also conservative. Right, and also, I mean, in the later on, I will also work with a larger class of formulae than just universally true sigma 1 formulae. Okay. Let me now say something about minimal elements in def and CDEF. So I would like to derive this from the following theorem, which is essentially an adaptation of a proof by Fyodor Pachomov and Albert Visser from a paper on a question of Krajewski's. And I would like to argue that the set of Gödel codes of truth definitions is not sigma 2 definable in the standard model. Actually, I suspect that this is by far not optimal. So probably one can show that this set is sigma 3 complete, but I do not have an argument at this point. And sigma 2 is, excluding sigma 2 is good enough for my current purposes. So suppose the contrary. And let sigma of x be a sigma 2 definition of the set of Gödel codes of true definitions. So as in the reasoning by Fyodor Pachomov and Albert Visser, we consider the following formula exists x delta of x, which is got from the via fixed point argument, which is equivalent to the statement saying that CT minus restricted to for every y less than x, not delta of y, that such a thing satisfies sigma, hence is a true definition. Okay, but this is not immediate that actually you can get it from the diagonal lemma. However, if you go through the proof, you will see that actually you can get more information. Actually, you can use it in this way to obtain such a pi1 formula delta. And my first claim is that if this holds, then exists x delta of x must be false in the standard model, and this is as in Fiedi and Albert's argument. So suppose not. Then actually by the fixed point equation, this thing, Ct minus restricted to for every y less than x not delta of y, is a truth definition. However, since exist x delta of x is true, we can pick the least number n such that delta of n holds. Hence, actually, in the standard model, for every y less than x not delta of y is equivalent to x is smaller than n, right? Because we have the least number for which delta holds. So for every less than n, delta must fail, so we have this. Okay, so hence such a theory, which is our definition of truth of arithmetic plus the set of true arithmetical sentences, this is just equivalent to Ct minus of n. So a statement saying that the truth predicate T satisfies Tarski clauses for sentences of depth at most n plus Th1. So it follows that this thing is a theory of truth for the language of Peano arithmetic, which contradicts Tarski undefinability of truth. Right? So actually, we concluded that exists x delta of x is false. So it follows that this thing cannot be a truth definition by the assumption that sigma defines def. However, at the same time, by sigma 1 completeness, EA proves not delta of n for every natural number n. Hence, actually, by my previous remark, eventually this turns out to be a definition of truth. Okay? And this is our contradiction. So actually, def cannot be sigma 2 definable. And let me continue. So as a corollary, you can show that if you have a sigma 2 definable set of definitions, then it cannot be dense in the structure in the sense that it cannot be the case that every truth definition is above an element of B. Right? And this is immediate since then.
Yes, yeah.
Sorry, are there a question? Is there a question? Maybe not.
J'ai essayé viking en espagnol.
Et alors?
Okay, I think we have.
En plus, c'est des vikings, genre en espagnol.
Thank you. Otherwise, the set of def would be the set of truth definitions which are above one of the elements of B. And this would be a sigma 2 definition of def. Right? So you are a truth definition if you can define, which is the sigma 1 condition, an element of B, which is sigma 2. So B cannot be dense. In particular, we get a corollary, once again, to Fiedi and Albert, that there are no minimal elements in the structure of true definition with definability ordering. And why? So how do we see it? So if we have a truth definition, then actually its singleton cannot be dense. So there is something which is not above alpha. There is a beta which is not above alpha. So actually you can then show that their disjunction is a definition of truth, because you can write a truth definition by saying that either alpha holds and then I'm using this formula, or alpha fails and then I'm using the other formula. This is a truth definition which is strictly smaller than alpha in this structure. Okay. So this is what was essentially proved by what was so this corollary actually was proven by in the paper by Fide and Albert. And now let me go to the main course for this MOPA, for me dinner, for you maybe more like a lunch, right, for some of you. So I would like to prove that this is a countably universal distributive lattice. And I'll prove this by showing that we can embed a countable atomless Boolean algebra in the structure. So we shall work with the following kind of truth definitions. So we take CT minus restricted to phi, and phi is essentially a formula which defines an initial which defines a possibly topped initial segment in a model, which includes all the standard cut to all the standard natural numbers. So these will be actually our truth definition. So we'll realize our embedding on a subset of this delta. And let me just remark that actually it is very easy to work with them because you can actually very naturally find suprema and infima of such truth definitions. So first of all, if you have two such truth definitions, then CT minus restricted to alpha and beta, and CT minus restricted to alpha or beta, they are both members of delta, so they correspond to taking the smaller out of two initial segments and taking the longer out of two initial segments. And the infimum, according in our ordering, in our ordering, corresponds to the disjunction of these two truth definitions. And if you think, what does it mean that we have CT minus restricted to alpha or CT minus restricted to beta, if both alpha and beta define initial segment, then this exactly means that we have CT minus a compositional truth predicate on the shorter one, on the intersection of their domain, so on the shorter ones. Okay, and it's also good because this is how typically in lattice theory you define, denote the infimum of two elements, and dually for the supremum. Right? And these operations are the same with the definability order as well. Okay. So now I will have two lemmata which show how to prove that actually, or maybe let me say it the other way. So I would say I will have two lemmata that would allow me to, in a sense, transfer some relations between alphas and betas from Lindenbaum algebras or Lindenbaum algebra for formulae for certain theories into the definability or ordering. So first of all, it is easy to show once again that actually if EA can prove that alpha is no longer than beta, then in CT minus restricted to beta, you can define CT minus restricted to alpha. Actually, I simply think that this truth predicate in CT minus restricted to beta simply satisfies CT minus restricted to alpha. So this is very easy. We have provability, in fact, in here. Slightly different. So we use the following thing. So if you have two members of delta for alpha and for beta, then CT minus restricted to beta defines CT minus restricted to alpha. If this holds, then CT minus extended with delta zero induction proves if alpha is the whole new universe, then beta is the whole of the universe. And as I've said, CT0 denotes the CT minus extended delta zero induction for truth predicate. So this is actually somewhat intriguing. So ideally, we would like to have like a single lemma for one theory, saying that one definition of truth defines the other. If something happens, something is provable if and only if something is provable in this theory. However, actually, we tried various things. We actually had some short discussion with our referee for this paper, and actually, I mean, this is not so easy because what is problematic is that satisfaction classes in non-standard models of PA can behave in a really pathological ways, like in particular contradicting our definitions from the standard model, where you cannot define a sigma 17 truth predicate, partial truth predicate, with a formula which is of complexity strictly smaller than sigma 17. It turns out, and it was observed by Bartek, we have a description of this in the appendix of our paper, and Bartek is Bartek Wcisło, that in a non-standard model of PA, we can have a partial satisfaction class which works for formulae of up to some non-standard depth, which actually can define a full satisfaction class for this model. So the point is that then the two satisfaction classes won't agree on their common domain. However, then this is possible, and actually, so the use of CT0 in here is to work with a better behaved truth class. Okay, so let me prove the incomparability lemma.
Oh, sorry. Go ahead. I was going to ask something, but go ahead. I want to see the proof first.
Okay. So suppose, aiming at the contradiction, suppose that CT minus restricted to beta defines CT minus restricted to alpha. However, CT0 plus for all x alpha of x and beta is not the whole universe is consistent. Then actually we can find a model. In the meantime, we use second Gödel's incompleteness theorem, that we have a model of CT0 plus statements saying that alpha is everything, beta is not everything, and moreover, this theory isn't consistent. Okay, so let me pick the least element such that we have not beta of C. And this is where we are using the assumption that beta is arithmetical. And let me define now a truncation of T. So T sub C, this is just a set of those formulae in the sense of M, which are true, and they are of depth at most C. Then there is one of the most important facts about the CT0, and actually the purpose why I chose we chose this for this incomparability lemma, is that actually this TC not only satisfies CT minus restricted to beta, and this is just by the choice of the C, but also we have full induction for this partial truth predicate. So this is one of the source of the strength of CT0. This is how actually non-conservativity of CT0 was first demonstrated by Bartek. That CT0 is like the union, an extension of a delta zero inductive truth predicate is a union of fully inductive restricted satisfaction classes or truth predicates. Okay, these are just our assumptions listed above. So we assume that CT minus restricted to beta defines CT minus restricted to alpha. Hence, actually, it means that in this model, M, TC, since we have CT minus restricted to beta and full induction, we actually have also a T prime, which is definable in this model, and so that it satisfies CT minus restricted to alpha and full induction. Full induction is because it is definable by some formula for this formula of full induction, and so on. So in particular, we have a fully inductive truth predicate in this model because our model satisfies for every x alpha of x. So everything is alpha. So this is not really a restriction in this model. However, then you can actually show that CT to CT0 is like a little bit, so CT is to CT0 is a little bit like PA is to I delta 0 plus X. In particular, CT can prove the consistency of CT0 with arbitrary true pi n sentence. And in our model, we have a proof of contradiction from CT0 and the true something sentence. Yeah, all of some standard complexity. Right. So this is a contradiction. Yeah, and we have the incomparability lemma.
Could you say again why this model has full induction in this language?
Why this model has the induction? Okay, so this is actually not obvious. I wanted to use it as a black box in this for these presentations. However, I mean, it was one of the key discoveries that helped us to show that CT0 is actually non-conservative over PA, which was first claimed by Kotlarski, but then there was a gap in the proof, and then actually Bartek shown that this is essentially by showing this. The idea is more or less that you can define a truth predicate for sigma C formulae. Okay, maybe this is so. Okay, so I can quickly recap on this. So let me maybe only find some space. So CT0, sorry. CT0 proves that whatever is provable in PA, then this is true. So in particular, for every non-standard in the model of CT0, in the model of PA, for every non-standard C, we can construct a formula which is a partial sigma C truth predicate, such that in this model we have prof PA phi is equivalent to sat sigma C of phi for every phi which is in the language of PA and of sigma C complexity. So from this it follows, sorry for the nonlinearity of this picture, that we have in a model of CT0, we know that for a fixed C, for every sigma C formula, we know that we have this equivalence, T of sat sigma C of phi. And then actually you can show that for this guy, you have full induction for this, sorry, for this whole formula, you have full induction because, sorry, too many phi's. If you have an arbitrary psi, which uses this predicate T of sat sigma C of X, then show that this is actually equivalent by compositional truth conditions to something like T of psi of sat sigma C. One more bracket. And actually this is delta zero. So for this guy, we have full induction. So for this guy, we have induction. So we have induction for this. And since psi was arbitrary, then we have full induction. Okay, so is this now the only black box is this, and that was conjectured by Kotlarski. There were some more technicalities involved. However, then I would like to hide this as a black box for this talk. Okay, so I will allow myself to do it.
Yeah, I think it's fine to keep that as a black book. But to recap what you just said, for myself, the gist of it is if T is delta zero inductive and C is any element of the model, then if you restrict T to formulas of depth at most C, then you have full induction with that predicate.
Yes.
Okay.
And I would say that if you would like to remember just one fact about CT0, then this is this model theoretical fact. Actually, you can prove various other things if you just remember this thing. In particular,
So C could be any element. It can go as high, right? There's no like it's a yeah. So you can define sort of cofinally high many truth approximations of the truth predicate essentially. Yeah. Okay.
Yes. Okay, so we have comparability and incomparability lemmata, and now let me show how do you actually embed a countable atomic Boolean algebra. So first we fix an elementary representation of such an object. For example, this can be the Lindenbaum algebra of propositional logic with countably many propositional variables. This is clearly elementary presentable and countable atomless. And this is how my embedding will look like. So I start with, so first of all, let me recall what are sigma 1 flexible formulae. So these are formulae that consistently over a theory, a fixed theory in advance, can be equivalent to any sigma 1 formula. So in other words, if you have a sigma 1 formula which is sigma 1 flexible over arithmetical consequences of this theory, then it means that this formula consistently over this theory can be equivalent to any sigma 1 formula. So for any given sigma 1 formula phi of y, it is consistent with this theory that eta and phi are equivalent. So these guys exist by the proof original due to Kripke, I believe. And this is a very tricky diagonal fixed point argument. It is, for example, you can find it in Lindström's book. Right, and these are the formula that will be restricting our CT-2. So for A in this algebra, we say that phi of A of x say that either CT0 is consistent up to x, so that below x there is no proof of inconsistency of CT0, or this fixed in advance flexible formula defines an ultrafilter on B which contains A. So I take this to be a canonical name for A, and you can clearly axiomatize the conditions on eta saying that it defines an ultrafilter on this Boolean algebra. And I will prove that if you send A to such a true definition, CT minus restricted to phi of A, then this is actually an embedding between lattices. Okay, so in particular, I will not preserve the complementation. I will not preserve the negation under this embedding, but I will preserve the lattice operations. And since countable atomic Boolean algebra is also is a universal distributive lattice, our claim will follow. Okay, so a remark. By the properties of ultrafilters, it is actually very easy to show that F, so defined, preserves infima and suprema, and this is why we are talking about ultrafilters. Why? Because if we have the supremum of A and B, so A or B, then any ultrafilter which contains A or B either contains A or contains B. Right? So it means that phi A of X or phi A of B, phi A of X or phi B of X holds. Right? And maybe I will say one more thing about how this phi of A behaves. So obviously, if you live in a model where CT0 is consistent, then each phi A is the whole universe. Interesting things start happening if we encounter the least proof of inconsistency of CT0. And then we check whether A belongs to the ultrafilter, which is in this model defined by eta, and whether eta defines an ultrafilter at all. And if this is so, then actually phi A of x contains all the greater numbers as well. However, if this ultrafilter does not contain B, then phi B of x might be just a topped initial segment, which ends with the least proof of inconsistency of CT0. Okay, let me continue. So we are very close to finishing. So this is not like a long argument from this point on. So we show injectivity. So it is enough to show that if A is not below B, so it's enough to show that if A is not below B, then CT minus restricted to phi of B does not define CT minus restricted to phi of A. So let me assume the contrary. So assume that A is not below B, but actually CT minus restricted to phi of B, to phi B, defines CT minus restricted to phi A. So by the incomparability lemma, it follows that this implication is provable in CT0. So if phi of A is everything, then phi of B is everything. Right? That was just the content of the incomparability lemma. Hence, by definition of phi of A and phi A and phi B, if we extend this theory further with not con CT0, so then in every model we have a proof of inconsistency. But this implication still holds because that was over CT0. Then actually this theory proves that if eta defines an ultrafilter which contains A, then this ultrafilter must contain B as well. So every ultrafilter which contains A contains B as well. I mean, which is already, we can see that where this is going. So if A is not below B, then we'll have an ultrafilter which separates them. Now the point is that we can actually define, since the operations of our Boolean algebras are sufficiently simple, so they are elementary, we can find a sigma 1 formula mi such that actually this formula will define an ultrafilter containing A intersected not B. So the infimum of A and not B. This is non-zero by our assumption in the Boolean algebra. So we can actually, in a fashion similar to Lindbaum construction, define via sigma 1 formula an ultrafilter which contains this guy. Yeah, so this is essentially an easy exercise. However, then this really ends our proof because we can then by the flexibility of eta, we can find a model of CT0 plus not con CT0. So of this theory, where actually eta is equivalent to me. Okay, and this will be our ultrafilter separating A and B. Okay, so this concludes my argument. So we have a function which is injective and preserves infima and suprema. So this is we have an embedding of the countable element Boolean algebra. Are there any questions for the proof? Because I have also some. I mean, if not, I will have some questions for you. Okay, maybe we can leave them also for later if you want. Right. So actually, this is a question of Albert, who's here with us tonight. So can we find a truth definition which is non-compositional in the sense that it does not define, say, the collection of all the no, sorry, this is not what I want to say, which does not define a truth predicate which is required to be compositional only on standard or on formula of standard depth. Right? So the trick is that this thing now is an infinite theory, so we cannot do such easy tricks as previously with finding smaller truth definitions and so on. And actually, I mean, this problem is on at least from 2019, 2020, I think. I thought about this intensively for some time. But there's I do not know, and I do not know in which direction should I go even with trying to answer this.
Can I say a little bit about the background of the problem? So the whole thing was that at some point you had the Davidsonian tradition, right? And so for them, the finite definability of truth was a kind of important thing for philosophical reasons. And so they really claimed that the aim of the truth definition was the Tarski biconditionals. So the fact that it should be finite, that dictated that it should be compositional. But this was never proven. And so in fact, this question is something like, is there a non-compositional truth predicate? So that was the background why I at some point started wondering about this question.
Yeah, and actually, I like this question really much.
Okay, that's it.
I would love to.
I mean, if this is true, then probably we can have like an essentially different truth definition, which is different from all that we know up to this point. Okay, but there are also some other questions. This is probably slightly more tractable. So is the set of truth definition a pi3 definable set? So I conjecture that it should be sigma 3 defined, sigma 3 complete probably. And there are some results from last year or 2 years ago, I don't remember, of co-authored by Albert, I believe also, that some problems connected to interpretability are sigma 3 complete. So this maybe there is a way of improving our claim that this is not sigma 2 definable in this way. And the last thing, there is a question whether, okay, so what are truth definitions? Or one of their purpose is to actually get not just truth, but finite axiomatizability of our favorite infinite theories. So in particular, you have a definition of truth, alpha, with some theta which serves as a true definition. Then alpha plus for all x, if x is an axiom of PA, then theta of x. Then this is, in natural example, a conservative extension of PA. However, all the situations we know is that actually such theories has a super exponential speedup over PA. This follows from the fact that they can define a consistency of PA on a definable cut, and then by some Friedman-Pudlak results, you can prove that they shorten proof significantly. So my question is that, is there a theory of this form which has at most polynomial speed up over PA, which is feasible in this sense? Okay, and that's it. So if you solve any of them, just please contact me. I'll be happy to know the answer.
Okay, let's thank our speaker. Thank you very much, Mateusz. It was great.
Thank you very much as well. It's always a pleasure to be at MOPA and speak at MOPA.
Of course, and it's great to have you. And are there additional questions? I know we asked a lot in the middle of your presentation.
I guess I know in the original paper you had some other questions. Do I take it those have been resolved, or?
Sorry, so could you repeat?
In the initial paper, you had a few other open questions. Do I take it some of those have been resolved, or? A couple
you mean
more?
Yeah, a couple of more. No, I just listed.
Okay, yeah. No.
The ones I find, I think the most interesting, probably. There was, I think, if I remember correctly, there was one question more about the structure, I think, of this ordering. Yeah, but I mean, it would be good to solve these ones first.
Oh, yeah, I'm not objecting to your choice of.
Okay.
Yeah. Nah, cheers.
Cheers.
Other questions? Okay, well, let's thank Mateusz again. Thank you
very much.
Mateusz.
Thank you for being here.
Thank you.
And just a reminder, next week, Leszek will be speaking, Leszek Kowaczyk. I apologize for my Polish. And the title and abstract will be up soon, but he emailed it to me today, so I can just read off. His title is Models of Fragments of PA with Low Scott Rank. So something on infinitary logic, L omega 1 omega. So it sounds very interesting. So again, same time, and we'll see you all next week. And that's the last meeting for the semester. Okay. Bye. See you all next week.
Yeah. Thank you very much. See you.